Hey Calc BC, welcome to lesson 6.7, alternating series part 2. We are nearing the end of our first unit covering sequences and series. This is lesson 10 from College Board's course description, alternating series error bound. So we're going to expand a little bit on our knowledge of alternating series from the previous lesson. We still have to go back and finish the ratio test from College Board's Lesson 8. We're going in a slightly different order, but by the end of Lesson 8, we'll cover all 10 of these topics from College Board. As I scroll down here, we can take a look at a little bit more depth of the alternating series error bound. The essential knowledge is, if an alternating series converges by the alternating series test, then the alternating series error bound can be used to bound how far a partial sum is from the value of the infinite series. And when we take a look at the notes, that will make sense. So let's head over in that direction. All right, so here we go. 6.7, alternating series part 2. Here's a description of the alternating series remainder. The first sentence is just taking a look at the just alternating series in general again. If a series has terms that are alternating, decreasing in magnitude, and having a limit of 0, we know that this series converges so that it has some sum S. So we're going to call the sum of this series capital S. If the sum S is approximated by the nth partial sum, S sub n, this notation has showed up before, but we've never necessarily written it. So we're going to start writing that now. S sub n is going to be the partial sum up to the nth term of the series, where we add only a certain number of the terms together. And if we have some partial sum, then the error in the approximation, absolute value of R sub n, which equals absolute value of S minus S sub n, will be less than the absolute value of the first omitted or truncated term. This capital R here stands for remainder. So basically what we're saying is that the error in our approximation, or the difference between the actual sum and our partial sum, is less than the absolute value of the next term in the series. In other words, if the three conditions are met, you can approximate the sum of the series by using some nth partial sum, S sub n, and your remainder, or your error, will be bounded by the absolute value of the next term, or the first truncated term, the first term that we didn't use. Okay, so that's a lot. I want to go back to our visual from the last lesson where we saw that because each value is smaller than the previous value that we're adding together, that's why we have to have some sort of convergent series that sums to S. And this lesson is now taking that one step further and saying that our final sum, our S, is within, the next term of the previous sum. So let me kind of explain what I mean here. Let's say we went 3 terms deep into this sum. So we added a sub 1, subtract a sub 2, add a sub 3. So right now we're here at S sub 3, the partial sum with just the first 3 terms of the series added together. If we take a sub 4, so the next term, which is this length right here, that term, the absolute value of it, is going to bound where our actual sum is. It's an error bound from S sub 3. So if I take a sub 4 and either subtract or add it to where S sub 3 is, the final value of S is somewhere in that range. And you can see it is, right here. And a sub 4 takes us all the way over here. So we're in the range. And that's because since our terms keep getting smaller and smaller, we're never going to get that much further away from the final sum again. Okay, so that is what's going on here. And so we're going to switch back to the notes. Give me 1 second. All right, so let's figure out what this actually means by doing an example. Given this series, approximate the sum S of the series by using its first 4 terms. So that's what we're going to do first. For letter A, we are going to say that the series is approximately equal to what we call S sub 4, which is the sum of the first 4 terms of the series. Okay, so I'm just going to plug 1 in for n, and then 2, and then 3, and then 4. So we'll have -1 to the 1 plus 1 over 1 factorial plus -1 to the 2 plus 1 over 2 factorial plus -1 to the 3 plus 1 over 3 factorial plus -1 to the 4 plus 1 over 4 factorial. And so that is going to be some sort of approximation of the overall sum of the series, but obviously it won't be the final value of the sum because we're only summing 4 terms, not infinite. So what happens here? We get 1 over 1 plus -1 over 2 plus 1 over 6, 3 times 2 times 1, plus -1 over 4 times 3 times 2 times 1, which is 24. And if we add all of these together, we're going to end up with 5/8 or 0.625. And in this question, you know, a decimal or a fraction would both be valid answers. So it does not matter. Either of those works. So that is an approximation of the sum. Again, that's not the actual sum, it's approximation. And so let's take a look at letter B. Use the alternating series error bound to show that this approximation differs from the actual value by less than 1 over 100. So our rule for alternating series error bound, as we saw up here, is that it is less than the absolute value of the first omitted term. So here's how we're going to write that. We're going to say the error in S sub 4 has to be less than or equal to the absolute value of A sub 5. So A sub 5 is just the next term in the series. And that term is going to tell us how much possible error there is in this approximation of the sum. So the absolute value of A sub 5 is going to be what? The absolute value of -1 to the 5 plus 1 over 5 factorial. That's the first term that we didn't write up here. And so that's going to be -1 to the 6 of 1 over 5 times 4 times 3 times 2 times 1, which is 120, which is just going to be 1 over 120. And the goal is to show that that error bound is less than 1 over 100. The denominator is bigger, so the error is smaller. So we have 1 over 120 is less than 1 over 100. Check. And part C, use your results to explain why S, the final value of the actual sum of all of these terms, is not equal to 0.7. So let's take a look. If we think about our approximation, which was 0.625 or 5/8, what this error bound is telling us is that if we add 1 over 120 or subtract 1 over 120, we're going to be finding the upper and lower bound of some region that the final sum lies in, okay? And if you've taken any sort of statistics class, this idea of error bound should be somewhat familiar to you. So we're going to end up with an upper bound of about 0.6167, a lower bound of 0.6333. That region is centered around 0.625. And the question said to use your result to explain why the sum of the series cannot equal 0.7. Well, look, we have a bound that does not include 0.7. So I'm going to write this out in a sentence. I'm going to say the maximum error in the approximation of the sum S sub 4, which was 0.625, is a sub 5, which we said was 1 over 120, which means the sum, or you could say the actual sum, is between 0.6167 and 0.6333. Therefore, S cannot equal 0.7. All right, so that's a valid answer. We are going to try one more question together here on the back. How many terms are needed to approximate the sum of this series so that the estimate differs from the actual sum by less than 1 over 1,000? Justify your answer. So what I'm going to do here is just start to write out the first several terms. We're looking for a term that is less than 1 over 1,000. And once we find that term, everything before that term is going to be our estimate of the sum, our partial sum that we're going to use. And you'll see once I write that out, in case that description verbally didn't help. So I'm going to start by just writing out this series. And let's just write out the first several terms. So we're going to have when n equals 1, that's going to be negative 1 to the second over 1 to the fourth. And then it's going to be negative 1 to the third over 2 to the fourth. And then it's going to be negative 1 to the fourth over 3 to the fourth, and so on. Okay, and what I'm going to do is start to figure out what is the absolute value of each one of these terms. So the numerator is going to be pretty meaningless. It's just going to be positive 1 or negative 1. So I'm really focusing on the denominator here. And this first one just equals 1. The second one equals 1 over 16. That's what 2 to the fourth is, 16. Next, we get 1 over 81. Next, we get 1 over 256. And I'm looking for the first fraction that's smaller than 1 over 1,000. So I didn't get there yet. So I'm going to write out another term. And that one's going to equal 1 over 625. Still not smaller than 1 over 1,000. So I'm going to keep going. And this one is 1 over 1,296. Okay, so that's the first term that's smaller than 1 over 1,000. So it would be really great if this term was our error bound, right? So what we're going to say is everything until that point is going to be part of our partial sum. And then the next term that's cut off would be our error bound. So the question again, how many terms are needed to approximate the sum so that the estimate differs from the actual sum by less than 1 over 1,000? We would say we want to approximate the sum using 5 terms. And then the next term is the error bound, which is less than 1 over 1,000. So that's how we do that question. And just to remind you, this idea of error bound in this way only works if we have an alternating series, which was the case in this question. The numerator caused the sign to keep switching. But there you go. So that's how you do that. Good luck with the homework, and let me know if you have any questions. Thanks for watching.